The objective today is to identify how household items use technologies to send, receive, or store information. Today you'll learn how bits are transmitted over the most common mediums: copper wire, fiber optic cable, and radio waves. Binary information must be encoded in some way before transmission over the internet. There are a few methods for encoding bits that are used far more often than others. Copper wire is used to transmit binary messages using electricity. A voltage on the wire means one state, and no or very low voltage means the other. Now, fiber optic cables, on the other hand, use light, that is on or off, to transmit a binary message. Your think, write, share right here is: why must binary information be encoded before transmission? Now, radio waves can be used to send binary information by altering the frequency or amplitude of the wave. Each method has benefits and drawbacks, which make it better suited for some situations over others. Together, these different systems form the network of bit sending devices we know as the Internet. A single bit sent from a cell phone in North America to someone in China probably travels over radio waves, fiber optic cable, and copper wire on their journey. Your think, write, share. What are the three methods that form this network of devices in this context of sending a message over to China? So here's the big questions first. I want you to keep these in the back of your mind as we're moving forward in today's lesson. Number one, for each medium, how is the information encoded? Number two, why are all three methods of sending bits used? And number three, why isn't there one best way of sending bits across the internet? Now, provide some instances when you'd want to use one method over the other. So let's start with something very simple: barcodes. These are 95 digits long, grouped into 15 different sections, which result in the number at the bottom of the barcode. Codes on the left are odd and to the right is even, so even if the barcode is upside down, the computer can adjust after scanning the item. There's a modulo check character to use to make sure that number is correct. That way, if you're scanning maybe frozen corn and there's a piece of ice on the barcode and it messes with the number, there's this modulo operation that goes on to make sure that that number checks out, because you don't want to scan frozen corn but pay filet mignon prices. And the other information on barcodes is the type of barcode, the manufacturer number, and a product number. So here it is all broken down. This is the formula for error checking, and if you use this formula on any barcode, you should see the number match up. The tricky part is the end, where you take the next highest power of 10 and subtract. So in this case, the next power of 10 is 30, because 23 goes into 30 only once, and therefore you have 7 remaining. So 30 modulo 23 is 7. And you can use this formula on any barcode and should be able to check to make sure I'm right. So the first digit right here goes here, and then the third digit and the fifth. Okay, so you see the pattern here. So you add all those together, times it by 3, then add what all the other numbers added up to, then you get 23 right here, then you have the modulo check character. So 30 modulo 23 would thus be 7 right there. If you want more barcode practice, you can go to this link. So your think, write, share here is, in your own words, you're basically explaining what I just did. Why does this image say modulo check character? I want you to watch another video today. This one does a much better job than I at explaining where barcodes came from. So your think, write, share through that is the first one: what is the machine reading when a barcode is scanned? What is UPC? What does QR stand for? And my favorite part, as the power of light reflection makes this all possible. If you are not in my class, you don't have to type the following. Just search for QR and barcodes explained as quick as possible. If you are in my class, I'll put this link right here up on Canvas for you to click on. Okay, so since I talked about barcodes, I might as well talk about QR codes, aka quick response codes. How much information can a QR code have? Well, QR codes are like balloons. They get bigger as you put more information in them. And like balloons, they do have a data volume limit. Other factors determining the size of a QR code are the selection of error correction, as well as the type of data encoding that is used. The max I've seen is 2.9 kilobytes, And over here is a threshold depending on how much you want to withstand damage. So if you have a sticker on a product, maybe a clothing product, if people are trying that clothing on often, you might have a very high damage rate. So that means your amount of data you can store on the QR code would have to be less. So usually, depending on that threshold for damage on the QR code itself, it will let you know. And right here you could see that error correction level, so it must be L since it's full solid black. Okay, so I'm going to try to perform a magic trick on you from the internet here through the video. So I want you to try to guess what I'm doing. Pretend this is Mr. H. So notice that I have a 6x6 layout here. So this is the part of the magic trick where I might add another row just for no reason at all, and I may look at it and do it very systematically. So we went from 5x5 right there to 6x6. And so now, closing my eyes, I can ask you to pick any card and flip it over. When I open my eyes, I will be able to easily tell you which one you had chosen. Can you, staring at this picture, staring at this pretend QR code, figure out how I'm able to do that? Are you detecting any patterns there on the board? So basically, this girl here is flipping over this card, right? When I open my eyes, I will be able to count the number of black cards in a row and see if it's odd or even. So right here, it is even. Over here, it is even. Now, if she's flipping one over in this row, I'm going to look and see that it's going to be an odd number, so I'll know that this one was the one that was flipped. And also I know it'll be the right one because there will be 1, 2, 3 black cards on this row, thus narrowing it down to that single one card that she had flipped. Right here, just as a final check to see if you're understanding what I explained with the magic trick, is this student using an odd or even type of parity to check for accuracy within a QR code? I won't read this part to you right here, but I know many of you are looking towards going to college and starting that long, crazy, frustrating process of buying textbooks. So you can pause it and read this part if you're interested in how this relates to purchasing your college books. And also pause a little bit on this slide if you're doing that ISBN research. So that's it for class today. If you want to further study this concept of checksums and how bits are being used even in your everyday household items, I recommend this book, The New Turing Omnibus. The parity method of error detection is relatively crude, and there are many other methods around that have better properties. Some of the more important ideas in error coding are Hamming distances, cyclic redundancy check, BCH codes, Reed-Solomon codes, and convolutional codes. Details about these sorts of codes can be found in Richard Hamming's book, Coding and Information Theory, and Benjamin Arazi's A Common Sense Approach to the Theory of Error Correcting Codes. The ISBN of Hamming's book is 01313913999. An interesting number for a book about coding. Less comprehensive but more accessible information about the error correction can be found in the Turing Omnibus to the right and in Computer Science and Overview by Brookshire. And then one last comment, Snapchat is using this as well. It just looks a little different. Snapchat introduced the QR codes for profiles in January 2015. They made it easy for people to add each other on Snapchat without typing in usernames. Here's your DOL, thinking back to copper wires, radio signals, and photons of light, then thinking about barcodes, QR codes, and snap codes. Why and how are these being used to send and receive and save bits? And one last question, why isn't there one best way to send bits?